Okay, so in this video, I just want to show how we could apply the previous theorem to help us find Laplace transforms. And then we'll jump into maybe proving why this theorem is true. But sometimes it helps us get a sense of why it might be true or how to use it when we start to take a look at examples. So here we know what the Laplace transform of cosine b of t and sine of b t are from the table that we've been using. But let's say, for example, all that we know is this. And along with this result that we have up here that we just showed on the previous slide. And now what we'd like to do is use this to figure out what is the Laplace transform of sine of b of t. So you might be thinking, how does this theorem even apply to this situation? Well, the reason why it does is because the sine of b of t is almost the derivative of the cosine of b of t. They just differ by a constant. Okay, so for example then, we can set our function f of t, in this case, that's going to be the cosine of b of t. And f prime of t isn't exactly the sine of b of t, but it's just off by a constant. So we would get minus b times the sine of bt. So in other words, the sine of bt, that's just equal to the derivative of f times minus 1 over b. So we could factor that minus 1 over b out. So let's start here. So what we want to calculate is the Laplace transform of of sine of b of t. And we can think of that to connect it to this theorem as the Laplace transform of minus 1 over b times f prime of t, okay, where f prime of t is the derivative of cosine. And we can pull out the constant multiple from inside the Laplace transform. So we can think about that as minus 1 over b times the Laplace transform of f prime. And therefore, using this theorem, the Laplace transform of f prime of t we just showed is going to equal s times the Laplace transform of f, we'll denote that with a capital F, minus f of 0 over here. So here we have applied the theorem where our function f of t is this. So now we've got minus 1 over b times the quantity s, and now we can use the fact that the Laplace transform of cosine is given over here. So we're going to get s divided by s squared plus b squared. So that we can use in place of the Laplace transform, and then we subtract f of 0, where our function f is the cosine function. So we're going to subtract the cosine of 0. So this doesn't quite give us what the table of Laplace transforms tells us we should get for the Laplace transform of sine of b of t. So we have a little bit of algebra that we can do. So if I distribute the minus 1 over b to both terms, I'm going to get a minus s over b times s over s squared plus b squared. And when I distribute this to cosine of 0, which is 1, we're going to get a negative 1 times a minus 1 over b. So we get a plus 1 over b. So this still doesn't quite look like the shortcut for the Laplace transform of sine of bt that we've seen in the table. So I can add these two fractions and put them over a common denominator. So I'm going to put them over the denominator of b times s squared plus b squared. So this s squared plus b squared comes from the fact that we would need to multiply this by s squared plus b squared, top and the bottom. And so now these s squareds cancel out, and all that's left is the b squared in the numerator, and one of these b's can cancel the b that's in the denominator. And now we get the formula that we have been using from that table of common Laplace transforms, that the Laplace transform of the sine of b of t is equal to b over s squared plus b squared. Okay, so now I'm going to just take a slight detour and prove this theorem that we've been using, and then we'll come back and look at how we can apply it to solve differential equations. So if you are curious about why this theorem that we've been using up here is true, that's what we'll take a look at in the next video or two.